Right now, gravity feels like the strongest thing in your world. It pins you to your chair, it makes a fall dangerous, it holds the moon in the sky. So here is something that should not be true. Gravity is, by an enormous margin, the weakest force in the entire universe. A cheap magnet can lift a paperclip against the pull of the whole planet Earth. Gravity is weaker than the electric force by a factor of 1 followed by 36 zeros. And yet that same feeble force is the one that builds the stars, the planets, the galaxies, everything enormous in existence. The strongest forces build only tiny things, atoms and molecules and you. The weakest force builds the biggest things there are. Tonight we are going to find out how that is possible and why it means everything out there had no choice but to be huge. Settle in and let the world go quiet. Subscribe if you haven't yet, because by the end of this, you will understand why you are small for the very same reason the galaxies are so large. Now, let's slowly slip into this. Part 1. The question you stopped asking. There is a question you almost certainly asked when you were very young, and then, at some point, quietly stopped asking. You were lying in the back of a car at night, maybe, watching the streetlights slide across the ceiling, or you were standing in a field far from any city, looking up at a sky absolutely crowded with stars, and you asked, in the plain and fearless way that only a small child can, why is it all so big? Why does it just go on and on like that? The grown-ups around you probably smiled and said something kind and a little vague, and you learned, the way we all slowly learn, that this was one of those questions that does not really have an answer. It was too simple. It was the kind of thing you were supposed to grow out of. You were told wrong. That question is not too simple to answer. It is one of the most profound questions in all of physics, and it does have an answer, a real one, with numbers and mechanisms and a chain of reasoning that runs from the size of the observable universe all the way down to the strength of the forces holding the atoms in your hand together. The reason nobody handed you the answer is not that there isn't one. It is that the answer is so unexpected and reaches so far down into the machinery of reality that most people never follow it to the bottom. Tonight, slowly, with nowhere to be and nothing to rush toward, we are going to follow it all the way down. Let me tell you where we are going to end up, so you can feel the shape of the journey before we take it. By the time this is over, the question, why is everything so big, is going to transform right in front of you into a completely different question. It is going to become the question, why is gravity so weak? And that second question is one that nobody on Earth can answer. So, we are not starting at a simple place and arriving at a simple place. We are starting at a question a child asks and arriving at one of the genuine unsolved mysteries at the edge of human knowledge. The two questions are the same question. That is the first strange thing, and we have a whole night to earn it. For now, just sit with how odd the bigness really is. We say the universe is big, but the word big has gone soft on us from overuse. We have heard the numbers so many times that they slide right off. The observable universe is about 93 billion light-years across. You have probably heard something like that before, and it probably did almost nothing to you because the number is too large to land. So let us not rush past it. A single light-year is the distance light travels in a year, moving at a speed that would take it around the entire Earth about 7.5 times in 1 second. Light is the fastest thing there is. Nothing can outrun it. And light, moving at that impossible pace without stopping, would need 93 billion years to cross the part of the universe we can see, except that it cannot even do that, because the space itself is stretching while the light travels. The number is not just large. It is almost aggressively large. Large in a way that feels like it is trying to tell you something. Let me try to wake one of those numb numbers up, just one, So it stops being a word and becomes a thing you can hold. We said the sun could swallow more than 1,000,000 Earths. Numbers like 1,000,000 have also gone soft on us from overuse, so let us slow it all the way down. If you wanted to count to 1,000,000 out loud, one number every second, without ever stopping to eat or sleep or rest your voice, it would take you about 11.5 days of continuous counting to arrive. Now imagine that every one of those counts was a whole planet Earth, an entire world with its oceans and its continents and everything that has ever lived on it, and you were dropping those worlds one by one into the sun. 11.5 days of dropping in a full planet every single second, and only then would that one average star be filled. And there are a few 100 billion such stars in our galaxy alone, and something like 2 trillion galaxies within reach of our telescopes. The bigness is not a single large fact. It is largeness stacked upon largeness stacked upon largeness, so many times over that the mind simply refuses the total and hands you back the soft, numb little word big instead. There is a temptation, when the numbers climb this high, to simply surrender to them, to say the universe is big and leave it at that, the way you would shrug at something too far away to ever touch. But I want to resist that shrug tonight, because hidden inside these numbers is a pattern, and the pattern is the real clue. The universe is not uniformly, boringly enormous from top to bottom. It is enormous in some very particular ways, and tiny in others, and the border between the two is surprisingly sharp. The atoms that make up the sun are among the smallest things that exist. The sun they build is among the largest. The very same matter, arranged 2 different ways, sits at opposite ends of the ladder of size. So the bigness is not really a fact about matter itself, because matter, we can plainly see, is allowed to be small. It is a fact about what happens to matter when a certain force gets hold of enough of it. Somewhere in the difference between a single atom and a star made of 10 to the 57th of them, the secret is waiting for us. And to find it, we first have to feel, honestly and slowly, just how many rungs separate the two. The bigness is not only out there at the scale of the whole cosmos, either. It is right here, close to home, in the ordinary objects of the night sky. Consider the sun, which is just a middling, unremarkable star, one of a few 100 billion in our galaxy alone. You could pour about 1,300,000 Earths into the volume of the sun and still have room left over. Our entire planet, everything you have ever known, every ocean and mountain and city and person who has ever lived, would be one small marble among more than 1,000,000 marbles inside that one average star. And that star is a speck. Set it against the galaxy it belongs to, and it vanishes completely. One dim grain of light among hundreds of billions, all of them turning slowly around a center so far away that the light leaving the sun tonight will need more than 25,000 years just to reach it. Here is what I want you to notice, and it is the thread we will follow the whole way. The bigness is not spread out evenly across everything. It is not the case that reality is simply built on a giant scale from top to bottom. Look closely, and you find that the truly enormous sizes are reserved for one very particular kind of object. Atoms are almost unimaginably small. You, standing in that field, are small. But stars, planets, galaxies, the great structures of the cosmos, those are colossal. Something decides which things get to be huge and which things stay small, and that something is not random. There is a rule underneath it. There is a reason the universe hands out its most staggering sizes to some objects and denies them to others, and once you see the rule, you cannot unsee it. It quietly rearranges the whole night sky. Most people, when they finally do ask why the universe is so big, reach for one answer almost automatically, and it is worth saying out loud right at the start, because we are going to have to take it apart. The answer is the Big Bang. The universe is big, people say, because it started with an explosion, and it has been expanding ever since, So of course everything is far apart and getting farther. You have heard this. It is even true as far as it goes. But it is going to turn out to be almost entirely beside the point, and understanding exactly why it misses the target is the first real step toward the answer. Because the expansion of the universe explains the distance between things, it says nothing at all about why the things themselves are so large. So this is the question, stated properly, the grown-up version of the one you asked in the dark all those years ago. Why does matter, left to itself in an expanding universe, gather into objects of such enormous size? Why is the smallest possible star, the very tiniest ball of gas that can actually catch fire and shine, still more than 300,000 times the mass of the Earth? Why are galaxies the size they are, and not 1,000 times smaller, or 1,000 times larger? There is a number, a single number, woven into the fabric of physics that sets the scale of nearly everything you will ever see in the sky. Tonight we are going to find that number, hold it up to the light, and then, at the very end, admit that we have no idea why it has the value it does. Let us start by feeling, honestly and slowly, just how big really is. Part 2. Climbing the ladder of size. Before we can ask why the universe is so big, we have to feel the bigness in our bodies, not just hear it as a number, and the best way to do that is to climb it one rung at a time. Imagine a ladder where every single step multiplies the size by 10, not adds 10, multiplies by 10. This is the only honest way to think about cosmic scale, because the sizes involved are so far apart that ordinary counting breaks down completely. So let us start at the very bottom, at the smallest size that means anything at all, and climb slowly upward, and I want you to keep a quiet count of how many rungs we pass, because the total is going to matter. At the very bottom of the ladder sits a length so small it barely deserves to be called a length. Physicists call it the Planck length, and it measures about 1.5 times 10 to the minus 35th of a meter. I will not even try to make that number feel real, because it cannot be made to feel real. It is the size at which our understanding of space itself dissolves, the smallest distance that has any meaning in known physics. Below it, the words length and distance simply stop working. That is our floor. That is rung 0. We climb. We pass through a long stretch of sizes with no name and arrive many rungs up at the proton, the tiny dense knot of matter at the center of an atom, about 1 times 10 to the minus 15th of a meter across. We keep climbing, another 5 rungs, and we reach the atom itself, about 1/10 billionth of a meter, which is mostly empty space, a whisper of a nucleus with a haze of electrons around it at an enormous relative distance. Keep going. Up through the scale of molecules, of viruses, of single cells, of grains of sand, and eventually, many more rungs up the ladder, we arrive at something familiar. We arrive at you, a human being about 1 meter in scale, standing in that dark field looking up. Now pause on that rung, because something quietly remarkable is true about where you are standing. You feel small when you look up at the stars. Everyone does. But on the actual ladder of sizes, from the Planck length at the bottom to the whole observable universe at the top, you are not near the bottom at all. You are close to the middle. You are roughly as many rungs above the smallest meaningful length as you are below the largest structure in existence. You are, in the truest mathematical sense, a middle-sized thing, standing at the balance point between the impossibly tiny and the impossibly huge. Hold on to that, because it is not an accident, and by the end of tonight, you will understand exactly why a creature that asks questions had to be a middle-sized thing. Let me linger on one rung of the ladder in particular, the atom, because it hides a bigness of its own that almost nobody ever feels. An atom is mostly empty. If you took a single atom and blew it up until its outer edge was the size of a large sports stadium, the nucleus at its center, where nearly all of the matter actually lives, would be about the size of a single grain of rice sitting on the center line of the field. Everything else, the entire enormous bowl of the stadium, would be empty space with only a faint mist of electrons somewhere out near the highest seats. This means that you, lying there in the dark, are almost entirely nothing. The solid, dependable body you have lived in your whole life is more than 99.999% empty space, held into a shape only by the electric forces reaching across all that emptiness. Even at the smallest scales, the universe turns out to be far larger and far emptier than it looks. A great deal of room wrapped around a very little matter. Now try to hold the whole ladder in your mind at once, all 60 rungs of it, from the trembling emptiness inside a single atom to the farthest galaxies at the very edge of what we can see, and notice how strange it is that any of it holds together at all. At every scale, something is quietly deciding how big things are permitted to be. Down among the atoms, it is the electric force drawing its tight, small, ferocious bonds. Far up among the stars and the galaxies, it is gravity drawing its enormous, patient, uncancelable ones. And somewhere in between, on roughly the rung where you happen to be standing, the two forces trade places, the electric giving way to the gravitational, the small giving way to the large. The exact rung where that handover happens, the size at which gravity finally takes command of matter, is the number we are hunting tonight. It is the reason the stars begin where they begin, and not somewhere far smaller. To find it, we have to stop admiring the ladder and start asking who built it, and the first name everyone offers turns out to be innocent of the crime. We keep climbing, and now the rungs start to open up into the sky. We pass the size of a mountain, of the Earth, which is about 1 1/3 times 10 to the 7th meters across, 13 million meters of rock and water and air. We climb to the sun, about 109 Earths wide, and then out past it to the whole solar system, and then we hit the light year, and the ladder changes character completely, because now each rung is a gulf that light itself takes years to cross. We climb to the scale of the Milky Way, about 100,000 light-years from edge to edge, a slowly turning wheel of a few 100 billion stars. And then we keep going, out past our galaxy, past the little cluster of galaxies it belongs to, out through the great filaments and walls where galaxies gather in their millions, until we reach the top of the ladder, the observable universe itself, about 93 billion light-years across. Now, the number I asked you to keep, from the Planck length at the bottom to the observable universe at the top, the ladder has about 60 rungs. 60 times you multiplied the size by 10, 60 orders of magnitude. That is the size of reality, expressed honestly. And the thing I want you to feel, lying there in the quiet, is that 60 is a shockingly large number of rungs. If the universe were simply built at a human scale, give or take, the ladder would have only a handful of rungs, and there would be nothing to explain. Instead, it towers upward through 60 factors of 10, and the objects that occupy the top of it, the stars and galaxies, are larger than you by a margin so extreme that no intuition can hold it. Somewhere on this ladder, something is generating enormous size, pushing certain objects up and up into a range that atoms and cells and human beings never touch. The question is what and where and why. Let me give you one more way to feel it, using not size but number, because it will matter later. Count the atoms in your own body. The answer is about 7 times 10 to the 27th, which is a 7 followed by 27 zeros. That is already a number beyond any real comprehension, more atoms in your one body than there are grains of sand on every beach and in every desert on Earth, many times over. Now count the atoms in the sun. The answer is about 1 times 10 to the 57th, a 1 followed by 57 zeros. The sun holds not twice as many atoms as your body, not 1,000 times as many, but a number larger by a factor of 10 to the 30th. That is the gap between a living thing and an average star, written in atoms. I want you to hold on to that middle number in particular, the 10 to the 57th atoms in a star, because it is going to come back in the strangest possible way. Right now, it looks like just another astronomical number, the kind of thing you measure by carefully weighing the sun. But it is not going to stay that way. Later tonight, we are going to derive that exact number, 10 to the 57th, from nothing but the strength of a single force. We are going to predict the size of a star without ever looking at one. And when a number you thought you had to measure turns out to be something you can calculate from the fundamental constants of nature, you have found the bottom of something. For now, keep climbing the ladder in your mind, feel the 60 rungs, and notice that the universe seems to save its most extreme sizes for the things built by one particular force. In the next part, we are going to deal with the answer everybody reaches for first, and see exactly why it is not the answer at all. Part 3. The answer that isn't an answer. The moment you ask seriously why the universe is so big, someone will tell you about the Big Bang, and they will say it with the confidence of a settled matter. The universe is big, they will say, because it began in an unimaginably hot, dense state about 13.8 billion years ago, and it has been expanding ever since. Space itself has been stretching for all that time, carrying the galaxies apart, so naturally everything is far away, and getting farther, it sounds complete, it sounds like an answer. And it contains a real and beautiful truth, so I do not want to wave it away. But I want to show you, carefully, that it answers a different question than the one we are actually asking, and the gap between those two questions is where the real mystery lives. Here is the truth the Big Bang genuinely does explain. It explains the distances between things. The expansion of space is real, and it is measured, and it does mean that two galaxies, which are not bound together, will drift apart over time as the space between them grows. So if your question is, why are the galaxies so far apart from each other, the expanding universe is a large part of your answer. The stretching of space over 13.8 billion years has opened up enormous gulfs of emptiness between the islands of matter. On that, the standard story is solid. Let me give you the picture that physicists themselves use for the expanding universe, because it makes the crucial point almost obvious. Imagine a loaf of raisin bread rising slowly in the oven. As the dough swells, every raisin drifts away from every other raisin, because the dough between them is expanding in all directions at once. That is the galaxies, carried apart by the swelling dough of space itself. But now fix your attention on a single raisin. The raisin does not grow. It is held together by its own stickiness, far stronger than the gentle rising of the dough around it. So while the space between the raisins expands, each raisin stays exactly the same size it always was. The galaxies are the raisins. The expansion carries them apart, but it does not puff them up. Whatever set the size of each raisin, it was not the rising of the dough, and whatever set the size of each galaxy, star, and planet, it was most certainly not the expansion of the universe. So the expansion is real, and it does a fine job explaining the emptiness between the galaxies, those enormous dark gulfs that light takes billions of years to cross. But it stands completely silent before the question we actually care about. It cannot tell you why a raisin is the size of a raisin. It cannot tell you why a galaxy is 100,000 light years across, rather than 100, or why the stars burning inside it are the size of stars, or why a planet is the size of a whole world. Every one of those objects is held together by a force, and anything held together by a force does not stretch along with the universe. Their sizes were fixed by something else entirely, something working patiently inside them, gathering them inward, deciding how large each one would grow. The Big Bang lit the fuse and laid out the smooth, thin fog of gas. But the sculptor who came afterward, the one who gathered that fog into every enormous object you have ever seen or heard of, was a completely different agent, and it is time now to name it properly. But now look closely at what that explanation does not touch. The expansion of space stretches the distance between galaxies. It does not stretch the galaxies themselves. It does not stretch you, or the Earth, or the Sun, or the Milky Way. Anything that is held together by a force, whether that is gravity holding a galaxy or chemistry holding your body, does not expand along with the universe. The space between bound objects is not growing, so the expansion of the universe has absolutely nothing to say about why any individual object has the size it does. It tells you the galaxies are far apart. It is completely silent on why each galaxy is 100,000 light-years wide rather than 100, or why the stars inside it are the size they are. The bigness of the objects is a separate question, and the Big Bang does not answer it. Let me sharpen this until it draws blood, because it is the pivot the whole night turns on. Picture the early universe, just after the Big Bang, before any stars or galaxies existed. It was almost perfectly smooth, a nearly uniform fog of hydrogen and helium gas, spread out through expanding space with only the faintest ripples of higher and lower density from place to place. That is the starting material. Now the question of bigness becomes very concrete and very sharp. Why did that smooth fog not just stay a smooth fog, thinning out forever as the universe expanded? Why, instead, did it gather itself into lumps? And why, when it did gather, did the lumps come out so enormous, a single lump becoming a star 300,000 times the mass of the Earth, a swarm of lumps becoming a galaxy of 100 billion stars? The expansion pulls matter apart. Something else pulled it together, and pulled it together specifically at gigantic scales. The Big Bang gave us the smooth fog. It did not make the lumps big. Let me say a word about how the smooth fog became lumps at all, because it is the very first act of gravity-building bigness, and it already contains the whole rule in miniature. In the early universe, the gas was almost perfectly even, but not quite. There were faint regions where the gas was a little denser than average, by perhaps 1 part in 100,000, the merest whisper of unevenness. And a region that is slightly denser than its surroundings has slightly more gravity, so it pulls in a little extra matter, which makes it denser still, which gives it more gravity again. Once it begins, it runs away with itself, the dense, growing, denser, gathering, and gathering across millions of years. That is how the fog curdled into clumps, and every star and galaxy you will ever see grew from one of those first faint ripples, pulled together out of very nearly nothing. But here is the part that matters most for our question. Gravity cannot make just any lump gather. A clump has to be large enough that its own feeble self-gravity can overcome the pressure of the warm gas trying to push it back apart. And because gravity is so weak, that minimum clump is already enormous, thousands of times the mass of the Sun before it will collapse at all. So even at the very first step, the opening act of all cosmic construction, gravity refused to work small. It gathered matter only in immense quantities, because immense quantities are the only thing a weak force can ever get a grip on. The lumps were born big, because the sculptor could not carve anything small. From that first moment onward, the bigness of everything that would ever exist was already decided by the same weak force we have been following all night, working in exactly the same way at the dawn of time as it does inside a star today. So the real question, the grown-up version of the one you asked as a child, is not about the explosion at all. It is about what happens to matter afterward. Why does matter, drifting in an expanding universe, clump together into objects of such colossal size? What is the force that does the gathering? And why does that force insist on working at such an enormous scale? That is the question. And notice how the frame has shifted. We are no longer asking about the beginning of the universe. We are asking about a force and about why that force builds big. The answer to why the universe is big is not going to be found in the first instant of time. It is going to be found in the character of the force that assembles matter, a force you have known your whole life and almost certainly underestimate. You already know which force it is. It is gravity. Gravity is the great gatherer, the only force that reaches across the enormous distances between scattered atoms of gas and slowly, patiently pulls them together into stars and planets and galaxies. Every large object in the universe was assembled by gravity, working against the thinning pull of expansion, drawing matter inward until it piled up into something. So if we want to know why the objects of the universe are so big, we have to understand gravity, and specifically, we have to understand one particular thing about it, one property that seems, at first, to be the exact opposite of what could possibly explain enormous size. Because the force that builds the biggest things in the universe is, by an almost absurd margin, the weakest force in all of nature. That sounds like a mistake when you first hear it. The force that assembles galaxies is the weakest force there is. It sounds backward, like saying the lightest person in the room is the one who lifts the heaviest weight. And yet, it is not only true, it is the entire secret. The weakness of gravity is not a problem to be explained away. It is the answer. The reason everything in the universe is so big is precisely that the force which builds those things is so pathetically, unbelievably feeble. Once you understand how weakness turns into size, the whole sky reorganizes itself in front of you, and you will never look at a star the same way again. I know that seems impossible right now, and it is supposed to. How could a weak force build big things while a strong force builds small ones? It runs against every instinct. So we are going to slow all the way down and take it in 2 careful steps. First, in the next part, we are going to establish just how weak gravity actually is. And the true number is so extreme that most people simply do not believe it the first time they hear it. And then, once the weakness is real to you, we are going to watch that very weakness force enormous size into existence, not as a paradox, but as the only possible outcome. Settle in. The force that holds you to the ground, the force you have felt every second of your life, is about to become the strangest thing you know. Part 4. The weakest thing in the universe. Gravity does not feel weak. This is the first obstacle we have to get past, because everything in your lived experience argues the opposite. Gravity is the force that pins you to your chair, that makes a fall dangerous, that gives the word heavy its meaning. It shaped every hill and shoreline you have ever walked across, and it holds the moon in the sky. When you are tired at the end of a long day, gravity is the thing you feel pulling on you. So to be told that gravity is the weakest force in nature sounds not just wrong, but almost insulting to your own senses. And yet it is true, and the gap between how strong gravity feels and how weak it actually is turns out to be the whole story. There are 4 fundamental forces in the universe, 4 basic ways that things push and pull on each other, and everything that has ever happened is some combination of the 4. The strongest is called, appropriately, the strong nuclear force. It is the glue that binds the tiny particles, called quarks, into protons and neutrons, and binds those protons and neutrons together into the nucleus at the center of every atom. It is ferociously powerful, but it has a strange limitation. It only works across distances smaller than an atomic nucleus. Reach any farther than that, and it vanishes completely. So the strongest force in nature is also, in a sense, the most short-sighted. It cannot see past its own nose. The second force is electromagnetism, and this is the one that runs almost everything in your daily life. Electromagnetism holds the electrons around every atom, binds atoms together into molecules, and therefore builds all of chemistry, which means it builds all of biology, which means it builds you. Every time you touch something solid, what you actually feel is electromagnetism, the electrons in your fingertips refusing to overlap with the electrons in the surface. When you sit in a chair and do not fall through it, that is electromagnetism holding you up. It is a strong force, only about 100 times weaker than the strong nuclear force, and unlike the strong force, it reaches across long distances. The third force, the weak nuclear force, governs certain kinds of radioactive decay and helps light the first spark of fusion inside stars, and it is much feebler still. We will not need it much tonight. And then there is gravity, sitting at the very bottom of the list, and the distance between gravity and everything above it is where your intuition is about to break. Let me give you the number, and let me give it to you slowly, because it is one of the most extreme numbers in all of science. Take 2 protons and ask how strongly they pull on each other by gravity, and how strongly they push on each other by electricity. The electric force between them is stronger than the gravitational force by a factor of about 10 to the 36th. Let me write that out. It is a 1 followed by 36 zeros. Gravity between 2 protons is not a little weaker than electricity. It is not 1,000 or 1,000,000 times weaker. It is 1,000,000 billion 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 times weaker. If you shrank the electric force down until it was the size of a single atom, gravity, on the same scale, would be smaller than the entire observable universe by a wide margin. That is not weakness. That is a kind of nothing that somehow still exists. Let me make that number touchable, because a figure that large just becomes noise otherwise. Take a small magnet, the kind that holds a photograph to a refrigerator door, a few grams of metal you could close your hand around. Hold it above a steel paperclip lying on a table, and let the paperclip jump up and stick to the magnet. Sit with what just happened, because it is quietly one of the most astonishing things you can witness. In that little jump, the magnet lifted the paperclip against the gravitational pull of the entire planet Earth. The whole Earth, 6,000 billion billion tons of rock and iron, every ounce of it pulling that paperclip down toward the floor, and a scrap of metal in your fingers overpowered all of it without the slightest effort, the entire planet pulling one way, a toy pulling the other, and the toy wins so easily it is not even a contest. That is the strength gap between electromagnetism and gravity, sitting there on your kitchen table, and once you have seen it, you cannot pretend gravity is strong ever again. Here is why gravity fools us so completely into thinking it is strong. You feel gravity powerfully, yes, but only because you happen to be standing on top of an object with the mass of an entire planet. It takes the whole Earth, every one of its 10 to the 50th atoms, pulling on you all at once, just to produce the ordinary, familiar weight you feel in your legs at the end of a long day. That is what gravity needs in order to make itself felt at all, a planet's worth of matter gathered beneath you. Electricity, by contrast, needs almost nothing. A plastic comb run through your hair on a dry day picks up enough electric charge to lift small scraps of paper up off a table, which means that comb is overpowering, once again, the gravity of the entire Earth pulling those scraps down. A trace of static on a cheap comb vetoes the whole planet. We mistake gravity for a strong force only because we spend our lives standing on a mountain of matter large enough to make even the weakest force in nature feel heavy. Let me hold the true number in front of you one more time, because everything else tonight is built upon it, and it deserves to actually be believed rather than just heard. Gravity is weaker than electricity by a factor of 10 to the 36th, a 1 with 36 zeros trailing after it. To grasp how enormous that gap is, imagine you had 10 to the 36th grains of sand. That many grains would not fill a bucket, or a room, or a city, or even a planet. It would be enough sand to fill our entire solar system, out past the orbit of the farthest planet, many times over. That is the size of the gap between the two forces, poured out in sand. Gravity is not a slightly quieter version of electricity. It is a single whisper set against a solar system full of shouting, one lonely grain against all that sand. And that whisper, that very nearly nothing of a force, is the one that turns around and builds the stars. Remember the shape of that sentence, because we will return to it when the whole night gathers itself together at the end. The weakest force in the universe builds the biggest things in it. So here is where we have arrived, and I want to state it as plainly as I can, because it is going to be the sentence we return to at the very end of the night. The weakest force in the entire universe is the force that builds the biggest things in it. Gravity, the runt, the force that loses to a refrigerator magnet, is the architect of stars and planets and galaxies and the great structures spanning the cosmos. Electromagnetism, hundreds of times stronger, builds only small things, molecules and crystals and cells and bodies. The force that loses every direct contest is the one that shapes the largest objects in existence. Any real answer to why the universe is so big has to explain that inversion, that upside-down arrangement where the feeblest force rules the grandest scales. And notice something about gravity in that little paperclip experiment, because it is the crack through which the answer is going to come. Gravity lost. Up close, in a fair fight, one-on-one, gravity always loses. It lost to the magnet. It loses inside every atom, where electricity rules absolutely. It loses inside your body, where chemistry holds everything together and the gravity between your own cells is so small it has never once been measured. Gravity loses every close-up fight it is ever in. Remember that, because it is only half the truth, and the other half is going to turn everything around. Gravity loses every fight but the last one. In the next part, we are going to find out how a force that loses every single battle still ends up winning the entire war. And the answer is going to explain, at last, why everything is so big. Part 5. How weakness becomes size. We are now standing at the center of the whole mystery, so let us not hurry through it. We have a force, gravity, that is almost incomprehensibly weak. Weaker than electricity by a 1 followed by 36 zeros. And somehow, that same force builds the largest objects in the universe. The resolution to that paradox is one of the most elegant ideas in all of physics, and it turns entirely on two special properties that gravity has and the other forces do not. Once you hold both of them in your mind at the same time, the bigness of the universe stops being a puzzle and becomes something close to inevitable. The first special property is that gravity never cancels out. To see why that matters, look at electricity, the strong force we keep comparing it to. Electric charge comes in two kinds, positive and negative, and opposite charges attract while like charges repel. This means that, in any large clump of ordinary matter, the positive and negative charges almost perfectly balance each other. Every atom has a positive nucleus and an equal negative cloud of electrons, and from any distance, the two cancel out. So even though electricity is enormously strong, a large body, like a planet, is electrically neutral overall, and it exerts essentially no net electric force on anything far away. Electricity is powerful up close, but it erases itself in bulk. It is a force that cancels its own strength the bigger things get. Gravity has no such off switch, and this is the thing to hold on to. Gravity comes in only one kind. There is no negative mass, no anti-gravity, nothing that pushes instead of pulls. Every scrap of matter attracts every other scrap of matter, always, with no exceptions and no cancellation. This means gravity adds up. Every atom in a cloud of gas pulls on every other atom, and none of that pulling is ever undone. So the more matter you gather, the more total gravity you have, without limit. Where electricity balances itself into silence at large scales, gravity just keeps accumulating. And that changes everything, because it means that gravity, weak as it is per atom, has a way to become strong that the other forces do not. It can win by sheer numbers. The second special property is that gravity has unlimited range and never gets saturated. The strong nuclear force, remember, switches off past the size of an atomic nucleus. But gravity reaches out forever, its pull weakening with distance, but never actually stopping. So every particle in the universe is, in principle, pulling on every other. Put those two properties together, and you have the recipe for the whole cosmos. Gravity is a force that never cancels and never quits. So no matter how weak it is for any two particles, if you pile up enough particles, the total gravity will eventually overwhelm anything standing in its way. Weakness per atom, multiplied by an enormous number of atoms, becomes overwhelming strength for the whole. Let me make the adding up concrete, because it is the mechanical center of the entire mystery. Picture two large clouds of gas drifting near each other in the dark of space. Every single atom in the first cloud pulls, by gravity, on every single atom in the second cloud. And since there might be 10 to the 60th atoms in a good-sized cloud, that is an almost unthinkable number of tiny individual tugs, all of them adding together, not one of them cancelling, because gravity simply has no opposite. 10 to the 60th feeble little pulls, summed, become a force strong enough to draw two clouds together across light years of empty space. Now try the very same thing with electricity. The two clouds are electrically neutral, made of equal parts positive and negative, so for every atom that pulls, another one pushes exactly as hard, and the entire enormous sum cancels away to almost perfectly nothing. That is the whole difference between the forces laid bare. Electricity is a shouting match in which the shouts cancel one another into silence. Gravity is a whisper in which every whisper adds to the last, until the sum of them is a roar that fills the universe. This is also why gravity is the force that governs the fate of everything large and everything lasting. The strong nuclear force is mighty but blind, past the width of an atomic nucleus. Electricity is mighty, but erases itself in bulk. Only gravity holds both of the properties you would need to rule the universe at the largest scales, unlimited reach, and no cancellation. And so only gravity is left standing when you ask what shapes a star, a galaxy, a whole cosmos. The other forces are sprinters, ferocious over tiny distances and vanishingly short times. Gravity is the one runner still on its feet at the end of the longest race there is, not because it was ever fast, for it is painfully slow, but because it never once stopped, never cancelled, and never tired. The universe at the largest scale belongs entirely to the weakest force, for the simple reason that it is the only force that just keeps adding up. And what it always adds up to, in the end, is bigness. There is an everyday version of this you can almost hold in your hand, and it makes the whole principle click into place. Think of a single drop of water. The forces holding that drop together, the electric bonds between its molecules, are so strong that gravity inside the drop is completely irrelevant. The drop keeps its shape because of chemistry, not because of its own weight. Now, imagine adding more water, and more, and more. For a very long time, nothing changes. The electric forces still rule, and the drop's gravity is still nothing at all. But keep going. Gather an ocean's worth, then a planet's worth, then far more than that, and at some enormous threshold, the gravity of all that accumulated water finally grows strong enough to crush the center and pull the whole mass into a sphere. The very same substance is governed by chemistry when there is a little of it, and by gravity when there is a mountain of it. Nothing about the water itself ever changed, only the amount changed. That is the entire secret of cosmic size held in a single image. Matter stays small when a strong force holds it together, and turns enormous when only the weak force is left to do the job, and the dividing line between those two worlds is always, without exception, huge. And now, at last, we can see why the universe has to be big. Because gravity is so weak, a small amount of matter produces almost no gravity at all. A handful of atoms, a rock, a boulder, even a small mountain, these things feel essentially no gravity of their own. They are held together by chemistry, by electromagnetism, not by their own weight. For gravity to become the boss, for it to take over and start crushing matter into a ball and heating it and running the show, you do not need a little matter. You need a staggering, astronomical amount of it. Gravity only wakes up when the pile gets huge. And so every object that gravity actually rules, every object where gravity has won, is necessarily enormous, because nothing smaller was ever big enough to rouse the weak force from its sleep. The bigness of stars and planets and galaxies is not a coincidence. It is the entry fee. It is the minimum size at which the weakest force finally becomes strong enough to matter. Let this settle, because it is the profound reversal at the center of everything. We tend to think big things are big because a strong force made them that way, the way a strong person builds a large structure. The truth is the exact opposite. Big things are big precisely because the force that made them is weak. If gravity was stronger, it would take hold of much smaller clumps of matter, and the objects of the universe would be tiny. Because gravity is so absurdly feeble, only gigantic piles of matter can trigger it, so everything gravity builds comes out colossal. The weakness and the bigness are not two separate facts that happen to sit side by side. They are the same fact. The size of the universe is a direct readout of how weak gravity is. Make gravity a little stronger, and the whole sky shrinks. Make it weaker, and the sky swells. There is something almost unbearable hidden in this, once you follow it all the way to the objects themselves, and I want to name it. The sun did not choose to be enormous. It did not grow to more than 1,000,000 times the size of the earth out of ambition or grandeur or any reason at all that we would recognize as a reason. Given how weak gravity is, nothing smaller than roughly the sun could ever have gathered enough matter to catch fire. The sun is the size it is because the laws of physics permitted no smaller shining thing to exist. Every star you have ever seen, every point of light in that crowded field sky from your childhood, was forced into its immensity by a number it never chose, a number written into the weakness of a single force. The grandeur of the night sky is not grandeur by design. It is grandeur by obligation. The stars are huge because they were not allowed to be anything else. In the next part, we are going to put an actual number on that obligation, and it is going to be a number you already met tonight. Part 6. The number hidden inside every star. The most beautiful result in this entire story came from a 19-year-old sitting on the deck of a steamship, and I love telling it because it shows you that the answer to why the universe is big is not vague hand-waving. It is a real calculation, and a teenager did it on a boat. In the year 1930, a young man named Subramanian Chandrasekhar was travelling by ship from India to England to begin his studies, and to pass the long days at sea, he worked on a problem that should have been impossible. He asked whether you could predict the mass of a star using nothing but the fundamental constants of nature, no looking at real stars, no measurements, just the basic numbers that describe how reality is put together, and pure reasoning, and it worked. Here is the shape of what he found, and you do not need the mathematics to feel the wonder of it, only the logic, which we have already built. A star is a battle between two things. Gravity is trying to crush the star inward, and because gravity never cancels and never quits, the more massive the star, the harder that inward crush becomes. Pushing back outward is pressure. The heat and the quantum resistance of the matter itself refusing to be squeezed into nothing. A star exists at the exact balance point where the inward crush of gravity is matched by the outward push of pressure. And the question Chandrasekhar asked was, at what mass does that balance happen? How much matter do you have to gather before gravity, the weak force, finally becomes strong enough to hold a ball of gas together and squeeze its core hot enough to ignite? The answer falls out of the constants, and it is this. The number of protons a star must contain before gravity can dominate its structure is approximately 1 divided by the square root of the gravitational strength cubed. That sounds abstract, so let me put the actual weakness of gravity into it, that tiny number we have been carrying all night, about 5.9 times 10 to the minus 39th. Run it through, and the answer that comes out is about 2 times 10 to the 57th protons. Multiply by the mass of a single proton, and you get a mass of very roughly 2 times the mass of our Sun. Sit with what just happened. Starting from nothing but the strength of gravity, a teenager on a boat predicted the mass of a star and got it right. The size of the biggest bright objects in the universe is not something you have to go out and measure. It is written directly into the weakness of gravity, waiting to be read. Think about how astonishing that really is, because it is easy to let it slide right past. There is no obvious reason, on the face of it, that the mass of a star should be predictable from first principles at all. You might expect stars to come in absolutely any size, a smooth and endless range from tiny to enormous, set only by the accidents of how much gas happened to be lying around when each one formed. And there is some spread, some stars heavier and some lighter. But they all cluster around the same characteristic mass, within a modest factor, the very mass Chandrasekhar found on his boat, and that mass is fixed by 3 numbers that have nothing whatsoever to do with any particular star. It is fixed by the strength of gravity, by the quantum rule that governs how tightly matter can be packed, and by the mass of the proton. 3 constants of nature, combined in one short calculation, tell you how large a star is required to be. The stars are not free to be whatever size they please. They are pinned by the most basic rules of physics to a scale they cannot escape. And this is the thing I most want you to carry out of tonight, so let me put it in the plainest words I have. The size of the largest bright objects in the universe is written into the strength of a force, not chosen, not accidental, written the way a conclusion is written into the premises of a proof, inevitable the moment the constants are fixed. Change the strength of gravity, and every star in the sky changes its size to match, obediently, instantly, because their sizes were never theirs to decide in the first place. The Sun is as large as it is because gravity is as weak as it is, and not 1 part in 1,000 of that could be otherwise. So when you look up at a star, you are not looking at an accident. You are looking at a fundamental constant of nature made visible, the weakness of gravity written across the sky in fire. Hold that phrase close, written into the strength of a force, because at the very end of the night it is going to grow far larger than it is right now, and take the whole universe along with it. And now the number returns, the one I asked you to hold on to back when we were counting atoms. That predicted count, about 10 to the 57th protons in a star, is the same number we quoted for the atoms in the Sun. Earlier tonight, it looked like a fact you could only get by weighing the Sun on some cosmic scale. Now you see that you never needed to weigh anything. You could have predicted it from the strength of a force. When a number you thought was a measurement turns out to be a calculation, you have reached the bottom of something real. The reason a star contains about 10 to the 57th atoms is the same reason the universe is big, and that reason is the weakness of gravity. The bigness of a star is written into the strength of a force. Hold that phrase, because we will return to it at the very end, and it will mean something larger than it does now. Let me take you inside the making of a star, so this stops being arithmetic and becomes something you can feel in your body. Imagine you could build a star by hand, one atom at a time, piling up hydrogen in the dark of space, and imagine you could feel the gravity of the growing pile as you worked. You begin. You add the first atoms, the first millions, the first billions, and nothing happens. Of course nothing happens. Gravity is far too weak to notice a pile this small. You keep stacking. You pass 1 trillion atoms, 1 trillion trillion, and still the growing ball just sits there, cold and dark and inert, feeling nothing, because gravity has not yet woken. You pile on more. You pass the mass of the Earth, an entire planet of hydrogen gathered in your hands, and the core barely stirs. You keep going. You pass the mass of Jupiter, more than 300 times the Earth, and now, finally, far down in the core, you can feel the faintest warmth, the first hint that gravity is beginning to squeeze. But it will not light. It is not nearly enough. You keep stacking tens of thousands of Earths, and the pressure climbs, and the core grows hot, and still no fire. And then, only when you have gathered roughly 80 times the mass of Jupiter, around 10 to the 57th atoms, does the core finally cross 10 million degrees. At that temperature, the hydrogen nuclei are slammed together hard enough to fuse, and fusion releases energy, and the energy makes light, and all at once, the enormous cold pile you have been building ignites and becomes a star. Light pours out into the dark for the first time, and what you feel, standing there as the builder, is the sheer immensity of what it took. Gravity demanded an ocean of matter before it would do anything at all. The star is not big because it wanted to be big. It is big because nothing smaller than this was ever allowed to shine. That is the number hidden inside every star, and it is the same number hidden inside the question you asked as a child. Part 7. The smallest thing that's allowed to shine. We have found the size of an average star, written into the weakness of gravity, and now I want to press on the lower edge of that idea because it hides one of the most quietly moving facts in all of astronomy. There is a smallest possible star. There is a hard floor below, which an object simply cannot catch fire, no matter what, and the existence of that floor tells you something profound about how strict the universe is with the privilege of shining. To be a star is not a gentle spectrum that fades away gradually toward nothing. There is a line, and you are either above it or you are not. Let me remind you of what has to happen for a star to shine, because the floor comes directly out of it. A star ignites when its own gravity crushes its core hot enough for hydrogen nuclei to fuse together, and that requires a temperature of about 10 million degrees. Gravity is what supplies the crushing, and we have already seen that gravity only becomes strong through accumulation. So the more mass an object has, the harder it squeezes its own core, and the hotter that core gets. A small ball of hydrogen squeezes its core only a little, and the core stays cool and nothing lights. You have to gather enough mass that the core crosses that 10 million degree threshold. And it turns out that the amount of mass you need is about 0.08 times the mass of our Sun. Put that in terms you can hold. 0.08 of the Sun is roughly 80 times the mass of the planet Jupiter, and Jupiter itself is already more than 300 times the mass of the Earth. So the smallest object in the entire universe that can truly ignite and shine as a star is still more than 300,000 times the mass of the Earth. Think about that. The dimmest, feeblest, smallest possible star, the runt of all runts, the least a shining thing is allowed to be, is still 250,000 Earths and more. There is no such thing as a small star, the way there is a small stone. The floor is astronomical. The minimum ticket to shine is an object beyond all human scale. Let me stay with the brown dwarfs a moment longer, the almost stars, because there is something in their story worth feeling rather than just noting. A brown dwarf is not a small star. It is an object that tried to become a star and could not, that gathered up as much matter as it could reach and still fell short of the line. Picture one of them, 60 times the mass of the planet Jupiter, enormous by any human measure, a ball of hydrogen so large it dwarfs every planet in our solar system, glowing a dull, sullen red from nothing but the leftover heat of its own gathering. For a while, early in its life, it can even fuse a rare and heavy form of hydrogen, flickering with a pale imitation of true starlight, but it can never light the main fire. Its core never quite crosses 10 million degrees. And so, over hundreds of millions, and then billions of years, it cools, and it dims, and it reddens, and finally it goes dark altogether, a star that never was, drifting alone and unseen through the space between the true stars for the rest of time. Let me also put the sheer height of that flaw in perspective, because it is easy to say 300,000 Earths and feel nothing at all. Our own planet is not a small object. It is nearly 8,000 miles across, with an interior of molten iron and a surface that has held every story ever lived. And yet, you would have to gather more than 300,000 entire Earths into a single ball before that ball could so much as begin to glow as the very faintest possible star. 300,000 whole worlds, each one a full planet, pressed together, and only then does the weak force of gravity finally have enough to work with to strike a light. That is the entry fee the universe charges for the privilege of shining. It is not a fee that any small thing can ever pay. It is a fee that keeps light reserved for the enormous, and it keeps it reserved so strictly precisely because the force collecting it is the weakest force there is. And here is where it becomes almost tender. What happens to the objects that do not quite make it? What about a ball of gas that gathers and gathers and reaches perhaps 50 or 60 times the mass of Jupiter and then simply runs out of material before it crosses the line? That object does not become a star. Its core never reaches 10 million degrees, the hydrogen never fuses, and it is left as something in between, too big to be a planet, too small to be a star. We call these objects brown dwarfs, and the older, sadder name for them is failed stars. They glow faintly for a while from the leftover heat of their formation, a dull ember of infrared light, and then, over billions of years, they slowly cool and darken and fade into the black, never having shone, never having lit their fire. They came so close. They were nearly a star, and they missed by nothing more than not being big enough. The line between a failed star and a true one is nothing but mass. It is not composition, not luck, not location. It is simply whether enough matter piled up in one place to wake the weak force and cross the threshold. Anything below 13 times the mass of Jupiter is planet-like and never even tries. Between 13 and 80 Jupiter masses, you get the brown dwarfs, the almost stars, the ones that failed. And only above 80 Jupiters, above that hard floor of 0.08 solar masses, does an object get to be a star and pour light into the universe for billions of years. The difference between a cosmos full of light and a cold, dark cosmos is nothing more than whether matter managed to gather in large enough piles. And that, once again, is a story about how weak gravity is. If gravity was stronger, the floor would be lower and much smaller objects could shine. Because gravity is so weak, the floor is set at 250,000 Earths, and only the truly enormous are permitted to burn. It is worth pausing on what lies just above that line, the smallest true stars, because they are strange and wonderful in their own right. A star sitting right at the floor, about 80 times the mass of Jupiter, is called a red dwarf, and it is the runt of all the true stars, dim and cool and red. But it holds a remarkable gift in exchange for its small size. Because it is so light, its gravity squeezes its core only gently, so it burns through its fuel with extraordinary slowness and thrift. A red dwarf can shine steadily not for billions of years like the sun, but for trillions of years, far longer than the entire current age of the universe. The smallest stars are the longest-lived, patient embers that will still be glowing quietly long after every large and brilliant star has died. Even here, size and fate are bound tightly together by gravity, the small burning slow and nearly forever, the enormous burning fast and dying young. So the whole life of a star, how brightly it shines and how long it lasts and how it finally dies, is set at the very moment of its birth by a single quantity, its mass, which is only another way of saying its size. Gather a little matter, just over the floor, and you get a dim red ember that will outlive the cosmos. Gather a great deal, up near the ceiling, and you get a brilliant blue giant that roars through its fuel and detonates within a few million years. Everything about a star follows from how much matter gravity managed to pull together to make it. And all of those masses, from the smallest red dwarf to the largest blue giant, are enormous by any human measure, because the weak force that gathers them cannot get started on anything less than 250,000 Earths. Size is destiny for a star, and the entire range of sizes is set, from floor to ceiling, by the weakness of one force. So the universe has an entry requirement for existence as a luminous thing, and the requirement is bigness. To shine, you must be huge. To gather the atoms that will become planets and, eventually, living things, you must first be a star, and to be a star, you must clear that astronomical floor. Every scrap of light in the night sky comes from an object that paid that enormous entry fee. The darkness between the stars is full of objects that could not pay it, the failed and the fading, the brown dwarfs drifting cold and unseen, and all of it, the shining and the failing alike, is decided by a single weak force and the enormous piles of matter it demands before it will do anything at all. In the next part, we are going to watch that same rule build everything else, because once gravity has made the stars set the scale for the entire rest of the universe. Part 8. Everything else inherits the scale. Once you understand why stars are enormous, the rest of the universe unfolds from it, one scale building on the next, like a series of rooms that each open into a larger one. The stars are the foundation, the first place where gravity truly won, and almost everything larger than a star inherits its scale from the stars, while almost everything we call a world is shaped in a star's shadow. So let us climb back up the ladder we descended, and watch how the bigness propagates outward from that first ignition. Start with planets, which form not on their own, but as a byproduct of making a star. When a giant cloud of gas collapses under gravity to build a star, it does not all fall neatly to the center. The cloud is turning, always turning a little, and as it shrinks, it spins faster and flattens into a broad disk, wheeling around the newborn star. Out in that disk, far from the central fire, dust and ice and gas clump together into the worlds, the planets, gathered from the leftovers of stellar construction. So a planet's scale is set by the disk, and the disk scale is set by the star, and the star's scale, as we have seen, is set by the weakness of gravity. Even the ground under your feet, the whole Earth, traces its size back through that chain to the same weak force. Worlds are the crumbs from the table where a star was built, and even the crumbs are thousands of miles across. Now climb upward instead of down, past the single star, and you reach the galaxy, and the galaxy is enormous in a way that once again comes from gravity, accumulating without limit. A galaxy, like our Milky Way, is not a handful of stars. It is a slowly turning wheel of a few 100 billion of them, bound together by their combined gravity across 100,000 light-years. Every one of those 100 billion stars pulls on every other, and none of that pull ever cancels. And so the whole immense structure holds together and turns as one. There is even more to it than the stars, because galaxies are held in the grip of enormous halos of dark matter, unseen material that adds still more gravity to the sum. But the principle is the same principle we began with. Gravity never cancels, so it adds up, and given enough matter, it binds structures of almost any size. A galaxy is simply what you get when gravity has an entire ocean of stars to work with. There is a twist in the story of galaxies that deserves its own moment, because it enlarges everything we have said about gravity and accumulation. When astronomers weighed the galaxies by their gravity, measuring how fast they spin, they found far more gravity than the visible stars could possibly account for, as though every galaxy were sunk inside an enormous unseen ball of extra matter. We call it dark matter, and we still do not know what it is made of, but we know beyond doubt that it is there, because its gravity is what holds the galaxies together, and the visible stars alone come nowhere near enough. For every pound of ordinary matter in the universe, there are roughly 5 pounds of this dark, silent stuff, and it too obeys the single rule that governs everything large. It gathers, it never cancels. It adds up, so the galaxies are held not only by the gravity of their stars, but by the gravity of a hidden ocean of matter many times larger still, and the scale of everything grows to match. Now pull back, as far as it is possible to pull back, until whole galaxies shrink to single points of light, and look at how those points are arranged, because it is the largest pattern that exists anywhere. The galaxies are not scattered at random. They are strung along immense curving threads, tens and hundreds of millions of light years long, called filaments, and where the threads cross one another, great clusters of galaxies gather into glowing knots. Between the threads lie the voids, enormous rounded chambers of near-perfect emptiness, hundreds of millions of light years across, holding almost nothing at all. The whole arrangement together looks uncannily like a web, or like the branching of nerve cells in a brain, a network of bright filaments wrapped around dark hollows. And every strand of it was drawn by gravity, working from the faintest ripples in the early fog, pulling the slightly denser regions denser still across billions of years, until the matter of the universe was combed out into this immense and delicate lattice. The largest structure in all of existence is a spiderweb, spun patiently by the weakest force there is. Let me lay the whole hierarchy out as a chain of numbers, because the way each scale contains the one below it is its own kind of wonder. A planet is gathered from the leftovers of a single star. That star is one of a few 100 billion bound together into a galaxy. That galaxy is one of perhaps 1,000 gathered into a great cluster. That cluster is a single knot in a filament of the cosmic web that stretches for hundreds of millions of light years. At every step, gravity takes the objects of one scale and binds enormous numbers of them into a single object of the next scale up. And at every step, the same weak force is doing the same patient work, never cancelling, always adding. The universe is built like a set of nested boxes, each one holding billions of the boxes below it, and the entire nesting was assembled by the force that loses to a magnet on a kitchen door. Notice that the bigness genuinely does cascade downward from the stars, not upward from us. The size of a galaxy is set by the number of stars it can gather, and the size of a star is set by the weakness of gravity, so the galaxy inherits its scale from the star, and the star inherits its scale from that one small number. Even the planets, even the ground beneath you, took their sizes from the disk of debris around a forming star, which took its size from the star, which took its size from gravity. Follow any object in the universe at any scale back through the chain of what gathered it and what gathered that, and you always arrive at the same place, the same small number, the strength of gravity. It is the root from which the entire tree of cosmic sizes grows, and every branch of that tree is large because the root is weak, and it does not stop at galaxies. Galaxies themselves are pulled together by gravity into clusters, groups of hundreds or thousands of galaxies bound into a single system. Clusters are strung together into enormous filaments and walls, and between the filaments lie immense empty voids, hundreds of millions of light-years of near-perfect nothing. Seen from far enough away, the whole universe takes on the appearance of a web, a network of glowing threads of galaxies wrapped around dark, silent voids, the largest pattern that exists. And every strand of that web was drawn by the same force that lifted a paperclip so poorly against a refrigerator magnet. Gravity, working patiently across billions of years and billions of light years, gathering matter into ever larger structures, never cancelling, never quitting, until the entire cosmos is threaded with its handiwork. Now, let me return to something I asked you to remember, because this is where it pays off. Back when we watched gravity lose to a magnet, I told you that gravity loses every fight but the last one. Here is the last one. Up close, in any single contest, gravity is pathetic. It loses, inside every atom, inside every molecule, inside your body, to a scrap of metal on a kitchen table. But zoom out. Give gravity the whole universe to work with, billions of years and unimaginable quantities of matter, and the force that lost every small fight quietly wins everything that matters. It builds the stars. It builds the galaxies. It draws the cosmic web. It decides the fate of the entire universe. The strong forces rule the small and the fleeting, the atom and the instant. But the weak force, the one that never cancels and never stops, rules the large and the eternal. Gravity loses every fight but the last one, and the last one is the whole cosmos. There is a lesson in that pattern that goes past physics, though I will only gesture at it and let you carry it where you like as you drift tonight. The thing that wins in the end is not always the thing that is strongest in the moment. Sometimes it is the thing that simply never stops, the patient and the persistent and the uncancelable, the force that is far too weak to win any single day, but that adds up, quietly, across an enormous span of time, until one day it has shaped everything. Gravity is the patient one. It waited, atom by atom, across the whole life of the universe, and it built the sky. In the next part, we are going to turn the question around completely and point it back at you, because the same rule that made the universe so big is the reason you are so small, and the two facts are about to become one. Part 9. Why you are so small. We have spent the whole night asking why everything out there is so big, and now I want to turn the question inside out and ask something you have probably never thought to ask. Why are you so small? Why is a living thing about the size it is, a meter or so, and not the size of a moon or a star or a galaxy? It sounds like a different question entirely, a biology question maybe, or no question at all. But it is the same question we have been asking all night, seen from the other side, and the answer is going to close a loop that has been open since we first climbed the ladder of size and noticed that you stand near its middle. Remember what decides the size of the objects each force builds. Gravity is weak, so it must accumulate enormous amounts of matter before it can do anything, and so everything gravity builds comes out colossal. Now ask the mirror question. What builds you? You are not held together by gravity. The gravity between the cells of your body is so faint it has never been measured and never could be. You are held together by electromagnetism, by the chemical bonds between your atoms, by the electrical signals racing along your nerves, by the electrons that refuse to let one molecule pass through another. Every process that keeps you alive and holds your shape together is electromagnetic, and electromagnetism, unlike gravity, is strong. Because the force that builds you is strong, it does not need to accumulate a colossal pile of matter to do its work. A strong force can hold a small thing together perfectly well. A chemical bond between two atoms is sturdy and reliable at the scale of a fraction of a billionth of a meter. It does not need to gather 250,000 Earths to become effective. It works fully and robustly at tiny scales. And so, The objects that electromagnetism builds, the molecules and the crystals and the cells and the bodies, are allowed to be small because the force building them is strong enough to matter, even when there is very little of it. Life sits at the scale where the strong, patient chemistry of electromagnetism rules, and that scale is small. So here is the closing of the loop, and I want to say it slowly, because it is one of those facts that quietly rearranges your sense of your own place in things. Your smallness and the universe's bigness are not two separate facts. They are the same fact, read from opposite ends. You are small for exactly the same reason the galaxy is huge. The strong force that builds you needs almost no matter, so it builds you small. The weak force that builds the galaxy needs an ocean of matter, so it builds the galaxy immense. One principle, the strength of the forces, sets both scales at once. You are not a small thing dwarfed by a big universe that has nothing to do with you. You are the small answer, and the galaxy is the large answer to a single question about how strong the forces are. You and the galaxy were written by the same law. Let me make the two scales actually meet in a single ordinary act so you can feel them touch. Lift your hand, right now, off the bed or the arm of the chair, just a few inches into the air. In that small and effortless motion, something quietly profound has just happened. The muscles of your arm, powered by electric and chemical forces, by electromagnetism, have just overpowered the gravity of the entire planet Earth, pulling your hand back down. Your arm won, easily, without strain, the way the refrigerator magnet won against the paperclip, and for exactly the same reason. The strong force that runs your body beat the weak force of a whole world without even noticing the contest. Every single time you lift a finger, you are reenacting the oldest imbalance in physics, the strong forces of the very small triumphing, up close, over the weak force of the enormous. You do it thoughtlessly, 1,000 times a day, and each time you are demonstrating the exact reason you are allowed to be small and whole, while the galaxy must be enormous merely to hold itself together. There is a strange comfort waiting in this, if you let yourself feel it as you lie there in the quiet. You are not an accident, stranded in a universe that has nothing to do with you, a tiny, fragile thing dwarfed by an immensity that does not know you exist. You are the small solution to the very same equation, whose large solution is the galaxy slowly turning over your head tonight. The forces that hold your atoms together and the force that holds the stars together are reading from one law, and that law wrote you at your size for the same reason it wrote the galaxy at its size. You belong to the pattern. The bigness above you and the smallness of you are not strangers to one another. They are two lines of a single sentence about how the universe is built, and you are one of the lines. When you look up and feel small, you are feeling, without ever having been told, your own place inside a law that also made the sky. And the smallness is not a diminishment. It is simply the shape that law had to give to anything intricate enough to look up and begin to understand it. Let me take you all the way inside it, so you can feel both scales in one body. Close your eyes, there in the dark, and imagine shrinking down into your own hand, past the skin, past the cells, down to where the atoms meet. Feel, at that scale, the grip that holds you together, the electromagnetic clasp between atom and atom, strong and tireless, and needing no size at all, a force so capable that a mere handful of atoms bound this way makes something solid and lasting. That grip is why you can be small and still be whole. Now rise back up, out of your hand, out of the room, up off the earth, out past the sun, out until the whole Milky Way lies below you, 100 billion stars turning slowly in the dark. Feel the force that holds all of that together, gravity, so weak that it needed every one of those 100 billion stars before it could bind anything at all. Same person, two forces, two scales. the tiny, fierce grip that holds your atoms, and the enormous patient pull that holds the galaxy. And you, standing at the balance point between them, near the middle of the ladder, are small for precisely the reason the galaxy is large. That is why a creature that asks questions is a middle-sized thing, the fact I planted back at the start and asked you to hold. You could not be built by gravity, because anything gravity builds is too enormous and too simple. A ball of gas or a wheel of stars, with no room for the intricate small machinery that thought requires. And you could not be much smaller than you are, and still be complex enough to wonder, because thought needs a great many parts arranged just so. So, a questioner sits where you sit, in the middle, small enough to be built by the strong forces into something intricate, large enough to hold a mind. The very fact that you are here, at your particular size, asking why everything is so big, is itself an answer to the question. You are middle-sized because only a middle-sized thing could ask. In the next part, we are going to find the edges of bigness, the places where even gravity's patient accumulation finally runs out, because bigness, it turns out, has a ceiling as well as a floor. Part 10, where bigness runs out. We have spent the night watching gravity build things bigger and bigger, so you might reasonably assume that bigness just keeps going, that with enough matter and enough time, gravity would pile things up without any limit at all. But that is not what happens, and the places where bigness runs out are just as revealing as the places where it begins. There is a ceiling on how big a star can be, and there is a ceiling on how big any structure in the universe can be, and both ceilings are written into physics as firmly as the floor was. Even grandeur, it turns out, is not allowed to be infinite. Let us start with the ceiling on stars, because it comes from a lovely reversal of everything we have said. All night, gravity has been the force gathering matter and building size. But once a star ignites, gravity suddenly has an enemy inside the star itself, and that enemy is light. A shining star pours out an enormous flood of radiation from its fusing core, and that radiation pushes outward as it streams toward the surface. In a small or ordinary star, this outward push of light is easily contained by gravity, but the more massive a star becomes, the more furiously its core burns, and the harder its own light pushes back. Keep piling on mass, and you reach a point where the star is producing so much light that the outward push of its own radiation equals the inward pull of its gravity. Past that point, the star cannot hold itself together. Its own light begins to tear it apart, blowing its outer layers off into space. This ceiling is called the Eddington limit, and it sets a maximum mass for stars somewhere in the range of 150 to 300 times the mass of the Sun. Try to build a star heavier than that, and it sheds the excess in violent outflows, refusing to exist above the line. So stars live in a band between the floor of about 0.08 solar masses, below which gravity cannot light them, and the ceiling of a few hundred solar masses, above which their own light destroys them. Everything that shines lives inside that narrow window, hemmed in below by the weakness of gravity and above by the fury of light. It is a remarkably strict rule for something as grand as a star. There is a smallest, a star may be, and a largest, and both edges are set by physics you now understand. The largest stars we know of live right up against that ceiling, and they pay dearly for it. There is a star catalogued with nothing but a plain string of letters and numbers, out in a neighbouring galaxy, that weighs on the order of 200 times the mass of the Sun, one of the heaviest ever measured. It does not live in serene grandeur. It burns through its enormous supply of fuel so ferociously that where the Sun will shine steadily for about 10 billion years, a monster like that will exhaust itself in only a few million, a single blink of cosmic time, before dying in a titanic explosion. And all the while it lives, it is shedding matter furiously from its surface, blasted off into space by the sheer pressure of its own light, as though the star were perpetually trying to tear itself apart and only barely holding on. The very largest stars are not stable, comfortable objects. They are things living right at the edge of what the laws of physics will permit, held just below the ceiling by nothing but their own violence. The end of greatness deserves one more moment too, because it says something quietly humbling about the reach of gravity. For 13.8 billion years, gravity has been gathering matter into ever larger structures, and you might reasonably expect that given all that time, it would have built something truly enormous by now, a structure spanning a large fraction of the whole universe. It has not. The largest coherent structures top out at a few 100 million light-years, which sounds immense, and is, but it is only a small fraction of the 93 billion light-years across the visible universe. Gravity simply ran out of time. The expansion of the universe pulls distant regions apart faster than gravity can draw them together. So beyond a certain scale, gravity loses the race, and no larger structure can ever form. Even the patient force that never cancels and never quits has a limit imposed on it from the outside by the stretching of space itself. Bigness has a ceiling not only for stars, but for the entire architecture of the cosmos, and that ceiling, like everything else tonight, is written into the numbers of physics. Now lift your eyes from stars to the whole universe, because there is a far larger ceiling, and it is one of the strangest facts in all of cosmology. We have watched gravity build ever larger structures, stars into galaxies, galaxies into clusters, clusters into filaments and walls. You might think this continues without end, structures, inside structures, all the way up. But it does not. When astronomers map the universe on the largest scales, they find that the building stops. Above a certain size, roughly 300 million light-years, there are no larger structures. There is no wall of walls, no supercluster of superclusters climbing forever. Beyond that scale, the universe simply becomes smooth, the same in every direction, a nearly uniform sea of galaxies with no greater pattern imposed on top. Cosmologists have a wonderful name for this. They call it the end of greatness. It is the scale at which greatness, in the sense of ever larger structure, comes to an end. Below it, the universe is lumpy and structured, full of galaxies and voids and walls. Above it, the universe is bland and featureless and everywhere the same. And that boundary matters enormously, because it means the universe is not infinitely structured. Gravity has had 13.8 billion years to build, and in that time, it has only managed to assemble structures up to a few 100 million light-years across, because beyond that scale, the expansion of the universe outruns gravity's patient gathering, pulling regions apart faster than gravity can draw them together. So even the great cosmic web has a maximum mesh size. Even the largest pattern in existence has an edge. Bigness runs out. There is something almost consoling in that, as you lie there in the dark, letting the scales wash over you. The universe is enormous, yes, immense past all telling, but it is not a runaway, not an unbounded nightmare of size, with no rules and no limits. It has a floor and it has a ceiling. The smallest shining thing is fixed by the weakness of gravity, and the largest structure is fixed by the race between gravity and expansion. Everything that exists lives inside those bounds, in a range that is enormous but finite, strange but lawful. The sizes of things are not arbitrary, and they are not limitless. They are set, top and bottom, by a handful of numbers woven into physics. And there is one more thing those numbers set, perhaps the most surprising of all, because the universe is not only big in space, it is big in time, and it had to be. That is where we turn next, and it is where the whole question finally comes home to you. Part 11. The universe had to be this big. We have talked all night about bigness in space, but there is another kind of bigness we have only touched, and it is the one that will finally bring the whole question back to you, personally, lying there in the dark. The universe is not only enormous in size, it is enormous in time. It is about 13.8 billion years old, and that great age is not a separate fact from its great size. The two are bound together, and the reason the universe had to be so old is the same reason it had to be so big, and both reasons come back, once more, to the patient weakness of gravity. Consider what it takes to make a single living thing, or a planet, or anything at all more interesting than plain gas. The Big Bang made almost nothing but the two simplest elements, hydrogen and helium. It made no carbon, no oxygen, no nitrogen, no iron, none of the elements that living bodies and rocky worlds are built from. Every atom of carbon in your cells, every atom of oxygen in the air you are breathing right now, every atom of iron in your blood was forged inside a star. Stars are the factories where the heavy elements are cooked, fused together in stellar cores over millions and billions of years, and then scattered back into space when the stars die, seeding the gas from which new stars and planets, and eventually, people are made. There is no shortcut. To build the atoms of a living thing, you must first run generations of stars, and stars are slow, and so the universe needed time, an enormous amount of it. It needed the first stars to form and live and die, enriching the gas with the first heavy elements. It needed second and later generations of stars to build on that, layering in more carbon and oxygen and iron. It needed, all told, billions of years of stellar life and death before there was enough of the heavy stuff to make a rocky planet with an atmosphere and oceans. Roughly 9 billion years passed between the Big Bang and the formation of our Earth. 9 billion years of stars being born and dying just to prepare the raw material. Let me walk you through what those billions of years actually contained, because the patience of it is staggering to hold in the mind. The first stars formed from nothing but hydrogen and helium, and in their cores they fused that hydrogen into helium and the helium into carbon and oxygen, building the first atoms heavier than the two simplest elements the universe had ever held. Then those first stars died, many of them tearing themselves apart in enormous explosions, scattering their newly forged elements out into the surrounding gas. From that seeded gas, a second generation of stars formed, and they built still heavier elements in their turn, and they too died and scattered their harvest into the dark. Generation after generation, the stars worked like a slow furnace running across billions of years, each cycle handing the next a little more of the heavy atoms that rock and water and living bodies require. The iron in your blood, the calcium in your bones, the oxygen crossing your lips at this very moment, all of it was assembled inside stars that lived and died long before the sun was ever born, and handed down to you across an almost unthinkable span of time. And none of that could be hurried, because the furnace runs only at the pace gravity sets, and gravity, as we have seen all night, is slow. A star like the Sun takes about 10 billion years to live out its life. The heavy elements had to be built across many such stellar lifetimes, and stellar lifetimes are long, precisely because gravity is weak and squeezes a star's fuel only gently, letting it burn at a patient, unhurried rate. So the very same weakness of gravity that forces stars to be enormous also forces them to be patient, to shine slowly across billions of years, which means the universe needed billions of years simply to manufacture the ingredients of a single living thing. The bigness of the universe in time is not separate from its bigness in size, and neither is separate from the weakness of gravity. It is all one story, told once with a ruler and once with a clock. A weak force builds slowly, and slowly, inside an expanding universe, means both very old and very large at once. The universe could not have made you quickly. The slow weakness of gravity that forces stars to be huge also forces them to be slow, and building the ingredients of life, took nearly the whole history of the cosmos. Now, put the two bignesses together and watch them become one. The universe has been expanding at nearly the speed of light for its entire history. So a universe that is billions of years old is automatically billions of light years across, because all that time the space has been stretching outward. You cannot have an old universe that is also small. Age and size are locked together by the expansion. And since the universe had to be old enough to forge the atoms of living things through generations of stars, it therefore had to be big, tens of billions of light years big, simply as a consequence of taking so long. The bigness in time forces the bigness in space. The universe is enormous in size because it had to be enormous in age, and it had to be enormous in age because gravity builds slowly and the ingredients of life take almost forever to cook. Let me take you to the moment it all began to turn, the first light in the history of everything. Picture the universe a few 100 million years after the beginning, and it is dark. There are no stars yet, no galaxies, nothing shining anywhere. There is only hydrogen and helium, cold and thin, drifting through an expanding blackness with no light in it at all. And then, slowly, in the densest places, gravity does its patient work. The gas gathers and piles up, until here and there across the darkness, the first clumps grow heavy enough to cross the threshold we watched earlier, and their cores ignite. And all at once, in the great dark, the first stars catch fire. The first light the universe has ever made pours out into the black. And with that light come the first factories, the first cores hot enough to begin forging carbon and oxygen and iron, the first atoms that will one day become worlds and oceans and eyes to see. You are watching, in that moment, the machinery that would eventually make you switch on for the very first time, and it needed an ocean of space and an age of time to do it. So here is where the whole night has been leading, the fact that turns the question around and points it straight at you. The very act of asking why the universe is so big required someone to ask it, and that someone required billions of years of stars, living and dying, to forge the atoms they are made of. And that in turn required a universe enormous enough and old enough to run the whole slow process to its end. You could not exist in a small young universe. There would be no carbon in you, no oxygen, no time for a planet to form and cool and grow life, and let that life become complex enough to wonder. The question and its answer are the same size. The universe had to be this big for there to be anyone here to notice that it is big. The bigness is not something separate from you, out there, indifferent. It is the precondition of your being here at all. You are made of the bigness. You are what it was for. In the last part, we are going to follow the question all the way to the bottom and find, waiting there, a mystery that no one has ever solved. Part 12. The question behind the question. We have come a long way from the child in the dark, asking why it is all so big, and we are almost home, so let us gather everything we have found and follow it to its final resting place. We began with a question that sounded too simple to have an answer, and we discovered that it does have an answer, and the answer is the weakness of gravity. Everything is big because gravity is weak. Gravity is so feeble that it can only build by accumulating enormous piles of matter. So everything it builds, the stars and the planets and the galaxies and the cosmic web, comes out colossal. The bigness of the universe is a direct readout of how weak one particular force is. That is the answer we came for, and it is a real one, and you can carry it with you. But a good answer in physics almost always opens a better question underneath it, and this one opens the best question of all. Because if everything is big because gravity is weak, then the natural thing to ask next is, well, why is gravity weak? Why is that one number, the strength of gravity, sitting down at a 1 followed by 36 zeros of feebleness compared to the other forces? Why is gravity not as strong as electricity or somewhere close to it? If gravity were as strong as the other forces, the whole picture we have built tonight would collapse. The smallest star would be a speck instead of 250,000 Earths. The sky would be crowded with tiny, fast-burning embers. The whole universe would be smaller, and it would live and die in a flash, far too quickly for planets to form, or life to arise, or anyone to look up and wonder about any of it. The size of everything you have ever seen hangs on that one number being as small as it is. And here is the quiet thunderclap that the whole night has been building toward. Nobody knows why gravity is weak. It is one of the genuine unsolved problems at the frontier of physics, serious enough that physicists have given it a name. They call it the hierarchy problem, the mystery of why the forces are arranged in such a lopsided hierarchy, with gravity so absurdly far below all the rest. There are guesses, there are hopes, there are ideas involving extra dimensions and undiscovered particles, but there is no answer. Let me tell you a little more about the mystery, because it is worth knowing that this is not a gap anyone is comfortable leaving open. Physicists do not merely lack an answer for why gravity is so weak. They find the weakness actively suspicious, almost offensive, because in their best theories, the strength of a force is set by many separate contributions added together, and there is no obvious reason those contributions should combine to leave gravity 36 orders of magnitude below all the others rather than roughly equal to them. It looks tuned, balanced on a knife edge, as if the number had been set with impossible precision and nobody can say by what. Some physicists suspect there are extra dimensions of space, curled up far too small to ever see, into which gravity quietly leaks away and dilutes its strength. Others suspect there are undiscovered particles waiting to explain the gap. Enormous machines have been built to go looking for these answers. So far, the universe has kept its secret entirely to itself. The weakness of gravity remains one of the sharpest unsolved problems in all of physics. And I find something wonderful in ending right here, at an honest edge, rather than at a tidy little bow. We set out tonight to answer a child's question, why is everything so big? And we did answer it truly and fully, all the way down to the mechanism and the number. Everything is big because gravity is weak. But that answer turned around and handed us a harder question that no one alive can answer, and that is not a failure of the night. It is the most honest place a curious mind can arrive, the exact spot where knowledge runs out and real mystery begins. The universe is under no obligation to explain itself all the way to the bottom, and it does not. It offers us one magnificent, readable answer, the weakness of gravity, and then, right underneath that answer, it keeps a single thing back, and that held back thing is written across the entire sky in the sizes of the stars. Every enormous object you will ever lay eyes on is the universe showing you, plainly and patiently, a number it is not yet willing to explain. We can measure the weakness of gravity to many decimal places. We simply cannot explain it. So the question, why is everything so big, the one you asked as a child and were told to grow out of, does not bottom out in a tidy answer. It bottoms out in a mystery that the smartest people alive cannot solve. Sit with the shape of that, because it is beautiful. The bigness of the universe, the thing that made you feel small in that field as a child, is the visible fingerprint of an invisible mystery. Every time you look up at the night sky and feel the size of it press down on you, you are looking directly at the consequence of a number that physics can measure but cannot justify. The stars are huge because gravity is weak, and gravity is weak for reasons no one understands. The grandeur of the heavens is not decoration, and it is not accident. It is the readout of an unsolved equation, written across the whole sky in light. You have been staring at one of the great mysteries of physics your entire life, every clear night, without knowing it. Let me gather the threads we have carried all night and lay them down together. We said near the beginning, that the weakest force in the universe built the biggest things in it, and it sounded then like a paradox, almost like a mistake. Now you know it is no mistake. It is the truest thing we found. The weakest force built the biggest things precisely because it was weak, because weakness forces accumulation, and accumulation forces size. We said that a star's mass is written into the strength of a force, and now you see that it is not only a star's mass, it is everything. The size of every object in the universe, the floor and the ceiling of bigness, the age of the cosmos, your own small stature standing beneath it, all of it is written into the strength of the forces, and the most fundamental of those numbers, the weakness of gravity, is one we cannot yet read the reason for. So the next time you find yourself somewhere far from the city lights, lying back and looking up at a sky absolutely crowded with stars, you might remember what the bigness actually is. It is not empty grandeur. Every enormous thing up there is enormous, because gravity is weak, and gravity's weakness is a mystery no one has solved. So the size of the sky is a question the universe is asking you as much as you are asking it. The child in the back of the car was not asking a foolish thing. She was asking one of the profoundest questions there is, and she was closer to the frontier of physics than any of the grown-ups who smiled and let it go. Why is everything so big? Because gravity is weak. And why is gravity weak? Nobody knows. Hold that gently as you drift off tonight, the way you would hold anything precious and unfinished. The universe is enormous, and the reason it is enormous is a secret it has not yet given up, and you get to fall asleep underneath the whole beautiful unanswered size of it.